The authors investigate the complex structure moduli dependence of scalar Laplacian eigenmodes for one-parameter families of Calabi-Yau n-folds in Pn+1, identifying the cause of eigenvalue crossing as related to complex multiplication on the torus. They speculate that this phenomenon is connected to rank 1 attractor points in arbitrary Calabi-Yau manifolds. To test this hypothesis, they numerically compute eigenmodes for the quartic K3 and quintic threefold, matching crossings to complex multiplication and attractor points. The numerical methods are validated by studying the dependence on the quality of the Calabi-Yau metric approximation, the number of points sampled, the truncation of the eigenbasis, and the distance from degeneration points in complex structure moduli space. The authors analyze the Fermat cubic, discussing discrete symmetries, eigenvalue analysis, and level crossing with enhanced symmetries. They introduce the concepts of complex multiplication and attractor points for the cubic CY1 fold, generalizing to Calabi-Yau n-folds. The numerical spectrum is computed using point generation and spectral analysis, supporting the connection between level crossing and complex multiplication, as well as the relation to attractor points. Calabi-Yau manifolds play a crucial role in string theory, enabling the reduction of higher-dimensional theories to lower-dimensional ones while preserving supersymmetry. The connection between Calabi-Yau compactifications and number theory was established by Moore, who observed that attractor points in the moduli space of these manifolds correspond to special points with complex multiplication. The authors review the relation between complex multiplication points and attractor points, arguing that it is more likely that crossings are related to attractor points. They describe their numerical analysis, approximating the Ruehle metric and the Laplacian eigenspectrum, and studying the influence of different approximation steps on the accuracy. The results of this analysis will be used to investigate the relation between attractor points and eigenvalue crossings. The authors delve into the intricate structure of the moduli space for a one-parameter family of Calabi-Yau threefolds, specifically the Fermat cubic. They demonstrate that this hypersurface admits a Ruehle metric and a nowhere-vanishing holomorphic one-form, which can be integrated over two one cycles to obtain the periods of the torus lattice. These periods are expressed in terms of hypergeometric functions, and the cubic is mapped into Weierstrass form using Nagel's algorithm. The Weierstrass equation is solved in terms of the flat torus coordinate, and the authors read off the modular invariants G2 and G3. The complex structure parameter tau is expressed as a function of the parameter, either using the hypergeometric functions or the Klein-J function. However, an analytic expression for tau only exists for special values of, and numerical formulae are required for general values. The authors identify special values of tau corresponding to specific values of, and note that only cubed enters the hypergeometric functions. They argue that a good coordinate on the complex structure moduli space is cubed rather than. The modular parameter tau is defined in the complex upper half-plane, modulo SL, 2, Z, transformations. For real, tau takes values along the boundary of the fundamental domain and along Re, tau, equals 0. The authors visualize the moduli space metric, which is constant along constant slices of Im, tau. In terms of, the moduli space metric is obtained from the periods or by inserting tau into the metric. The resulting metric is plotted, with color coding matching the metric on the fundamental domain for tau. The authors highlight the importance of understanding the complex structure moduli space, particularly in the context of Calabi-Yau threefolds. In the subsequent sections, the paper discusses the symmetry group of the cubic hypersurface in the context of complex structure moduli space. The symmetry group is a semi-direct product of S3, Z3, and Z2, with S3 being generated by cyclic permutations and transpositions, Z3 by the action of the scalar Laplacian, and Z2 by complex conjugation. The dimensions and numbers of irreducible representations, IRREPs, of the symmetry group are calculated using the software gap in SAGE and presented in Table 1. The eigenvalue analysis of the scalar Laplacian on the torus is also discussed, with eigenvalues given by equation 18, and corresponding eigenfunctions by equation 19. These eigenvalues are plotted as a function of the complex structure parameter in Figure 2, showing a similar behavior to the quintic case, 30. The multiplicity of coincident eigenvalues in complex structure moduli space agrees with the dimensions of the ERIPs of the symmetry group, but at k-dimension 1 loci where eigenvalues cross, the symmetry group does not enhance, and the multiplicities do not fall into ERIPs of the symmetry group. The paper also addresses the question of what is special about the crossing points in the following sections. For the torus, there is analytic control over the spectrum, and expanding equation 3 around large gives the resultant equation 20. This research paper delves into the analysis of the Laplacian spectrum on Calabi-Yau manifolds, specifically focusing on the interplay between complex structure, symmetry, and the Laplacian spectrum. The study explores the behavior of eigenvalues as a function of the complex structure parameter, revealing that they arrange in ERIPs of the symmetry group and are governed by the overall volume factor. For purely imaginary values of the complex structure parameter, modes associated with the A cycle become lighter as the B cycle volume and overall psi volume grow, while modes associated with the B cycle exhibit constant behavior due to a cancellation between volume and winding factors. Modes that wrap both the A and B cycles also become lighter as the complex structure parameter approaches infinity, attributed to the competition between 2-3 cycles in the T3 fibration of the quintic. Level crossings and enhanced symmetries are observed away from the point of maximal unipotent monodromy, with enhanced symmetries present at specific points such as =0 and =2 due to an SL(2)Z transformation on the hypersurface. Two modes cross when the complex structure parameter corresponds to algebraic periods, which are special points in terms of the hypersurface but not the defining equation. These findings contribute to a deeper understanding of the interplay between complex structure, symmetry, and the Laplacian spectrum on Calabi-Yau manifolds, shedding light on the swampland distance conjecture. The paper also investigates rank 1 attractors and complex multiplication for tori and K3 surfaces, as well as their relationship with the appearance of rational periods. It discusses the case of tori, where rank 1 attractors, complex multiplication, and the appearance of rational periods are closely related. The paper introduces the concept of a binary quadratic form in two variables with integer coefficients, q, x, y, equals x squared plus bxy plus psi squared, and its discriminant d equals b caret 2 for ac less than 0, which remains invariant under SL(2)Z transformations. The number of orbits of this action, or the number of equivalence classes of binary quadratic forms up to SL(2)Z transformations, is called the class number and denoted by H(d). The paper then moves to elliptic curves, mapping onto C equals C, Z squared, where Z squared is a z-lattice. It explains that for a generic elliptic curve with coordinate W squared, the endomorphisms of the elliptic curve to itself that fix the origin are holomorphic maps of the form W greater than A, where A belongs to the lattice. A generic torus has an endomorphism given by multiplication with an integer A and Z, corresponding to integer scalings of the lattice. However, if we choose a lattice generated by 1 and tau, where tau belongs to Q, sqrt, d, we have an additional endomorphism given by multiplication with A equals D plus sqrt, D, 2, and end, E, equals Z, A, Z, where A is the coefficient in front of the quadratic term in the binary quadratic form. Such elliptic curves have complex multiplication by A. This research paper explores the concept of complex multiplication, CM, in the context of Calabi-Yau manifolds, specifically focusing on tori and K3 surfaces. It begins by introducing CM for elliptic curves, which are unidimensional Calabi-Yau manifolds, and explains how they lead to non-trivial endomorphisms of the elliptic curve. The paper then generalizes this concept to higher dimensional tori, T2n, where an endomorphism A is defined as a linear transformation that preserves the lattice of periods. The existence of such endomorphisms is shown to depend on the solvability of the equation T(Tn plus T(Tmn T(T)m T equals 0, where T is the period matrix, and M, N, M0, N0 are integer matrices. The paper also delves into the case of K3 surfaces, which are two-dimensional Calabi-Yau manifolds. A K3 surface is of CM type if its transcendental lattice T is of CM type, meaning it has a unique holomorphic 2 form, and T is a two-dimensional vector space over a quadratic CM field. Attractive K3 surfaces, which have Picard rank 20, admit non-trivial endomorphisms of their middle cohomology, corresponding to multiplication by elements in an imaginary quadratic field. These K3 surfaces can be constructed as double covers of the orbifold T2T2, Z2 and inherit the CM property from the underlying twitori. Furthermore, the paper discusses the one-parameter family of quartics in P3, which have Picard rank 19 generically but can be enhanced to 20 over a dense set of countably many points in the moduli space. The Picard-Fuchs system of the quartic is also hypergeometric, with the fundamental period given by a specific hypergeometric function. This raises the question of whether there will be crossings in the spectrum of the Laplacian at these points of enhanced symmetry, similar to the torus case. In addition, the paper examines the quintic Calabi-Yau threefold, which exhibits CM at special points determined by calculating the corresponding values from the modular parameter. The period matrix elements can be obtained from the prepotential F, and the existence of CM is equivalent to the condition that the elements of the endomorphism matrix generate an imaginary field K. Borsia proved that this number field must have degree 2, H2, 1 plus 1, and Gakov and Vafa showed that the Fermat quintic satisfies this condition for equals 0. The period matrix elements take values in the extension Q, eta, where eta is the fifth root of unity, and the endomorphism matrix A is also valued in this extension. The elements of T and A satisfy the condition that they are both valued in K equals Q, eta, in accordance with Borsia's result. Numerical analysis reveals level crossings at the CM point equals 0, but no other CM points are known for the quintic, and there is some evidence that none exist. Finally, the paper discusses the attractor mechanism, which states that vector multiplets coupled to spherical, dionic black holes flow to fixed points in their target space. In the context of IIB string compactifications on Calabi-Yau manifolds, the vector multiplet moduli space is associated with the complex structure moduli space, and the charge lattice is given by the middle cohomology lattice. The fixed points of the attractor flow for a black hole with charges correspond to a condition on the Hodge structure of X. The normalized central charge of the BPS black hole is given by an expression involving the complex structure moduli-dependent holomorphic top form and the Poincaré dual to the charge. Stationary points of the central charge occur if and only if the charge has a specific decomposition. The attractor flow equations can be simplified by redefining the inverse radial distance, and the flow ends at stationary points of the central charge. To compute the attractor points, one proceeds by defining the quantum-corrected volume of holomorphic event-dimensional cycles in the mirror dual IIA theory. The discussion revolves around the relationship between complex multiplication, CM, points, attractor points, and arithmeticity in Calabi-Yau, psi, manifolds. The authors investigate a one-parameter family of quintics where periods and complex structure coordinates are not expected to be arithmetic. They resort to numerical methods, computing the spectrum of the scalar Laplace operator on the psi manifold using techniques from 22 and the symmetric package 26, 27. To correct for over or undersampling regions, weights are assigned to points based on the ratio of the pullback of the ambient space Fubini study, Fs, metric and the volume measure on the Cy as computed from $J, tau, $2. The correlation between void regions and the curvature of the pulled-back Fs metric is observed. The numerical computation of the spectrum of the Laplacian on the psi hypersurface is performed using the pullback of the Fs metric and the exact psi metric obtained from $J, tau, $2. The results are compared to the analytic result, 18, to quantify the error of the approximation. The spectrum is computed for various numbers of points, $n_p$, complex structure parameters, $tau$, and numbers of basis functions, $k$. The first 36 massive eigenmodes, averaged per multiplet with error bars, are plotted in Figure 4 as a function of the number of points for the Fs and the exact psi metric. The metric dependence is observed to be weak, and the error from using the Fs metric is comparable to the error for the exact psi metric. This study aims to understand the connection between attractor points and level crossing, as attractor points are related to BPS objects. It also investigates the influence of hyperparameters on the spectrum approximation, which will be useful for future studies involving higher Laplacian eigenmodes. The authors investigate the eigenmodes of the scalar Laplacian on a Calabi-Yau psi manifold, comparing the exact psi metric with the pullback of the Fubini study FS metric. They compute the spectrum using 100k points and k equals 3 for the first 12 multiplets, varying the complex structure and the number of basis functions. Figure 5 shows the first 36 massive eigenmodes as the complex structure is varied, with error bars corresponding to one standard deviation. The exact psi metric agrees well with the analytic result, while the FS metric result starts to deviate from the other two around the 8th heaviest eigenmode. The authors find that for lower eigenmodes, as few as 1000 points and the FS metric already give good agreement with the exact result, but for higher eigenmodes, 10k points are needed, and 100k points are necessary to obtain agreement with the analytic result after reaching the 8th heaviest multiplet. The basis for the ambient space eigenfunctions is given by equation 59, which involves monomials of degree k in the homogeneous ambient space coordinates. Error analysis reveals that using k equals 2 eigenmodes provides good approximations up to the 8th multiplet, after which finite truncation effects become significant. In contrast, k equals 3 and k equals 4 provide excellent approximations, with the latter comprising the first 225 ambient space eigenmodes. The metric dependence is weak, but pronounced for k greater than 2, where the error due to the approximated metric becomes the main source of discrepancy between numerical and exact results. The numerical analysis of crossings and attractor points is performed using the methods outlined in section 4. For the torus, the crossings of eigenmodes of the scalar Laplacian are compared to the known Calabi-Yau psi points on the underlying manifold. For the quartic, the one-parameter Fermat quartic has a symmetry group S4, Z4 times Z4, and the spectrum of the scalar Laplacian is analyzed as a function of complex structure. Eigenvalue crossings are observed in the vicinity of psi points. The irreducible representations, IRREPs, are found using the same method as for the torus, and the approximate psi metric is used to compute the spectrum, giving access to the first 100 eigenmodes of the scalar Laplacian on P3. Analyzing the behavior of eigenmodes of the scalar Laplacian on Calabi-Yau psi n folds. This research focuses on explaining observed behavior in the quintic case, where some eigenvalues become heavier while others become lighter as the complex structure varies, leading to eigenmode crossings along special loci in the complex structure moduli space. Gaining analytic control over the spectrum in the psi one-fold case, the Ricci-flat CY metric is simply the flat metric, allowing computation of eigenfunctions and eigenvalues in terms of winding numbers around the torus periods. The eigenvalues are given as a function of the complex structure modulus, with crossings occurring along a real codimension 1 line in the complex structure moduli space, specifically at complex multiplication (CM) points. Generalizing the notion of CM points to arbitrary psi n folds, the authors formulated as a condition on the middle cohomology lattice. For T2 and K3, CM points are closely related to attractor points in complex structure moduli space, but in general, the two are distinct. The authors argue that crossing points are more likely to correspond to rank 1 attractor points rather than CM points, as the latter are scarce, while the number of crossing points is infinite. Numerical computations of the eigenspectrum on K3 and the quintic show that crossing points correspond to attractor points, which is surprising since attractor points are related to BPS objects, while higher eigenmodes of the Laplace operator are not. The authors solve the attractor equation for the quintic and show that a D-brane system leads to attractor points compatible with the crossing points, shedding light on the connection between eigenmode crossings and attractor points in the central charge function for general n-folds. The authors draw upon a vast array of research in mathematics and physics, citing works on numerical metrics for complete intersection Calabi-Yau manifolds, Calabi-Yau metrics with jacks, and the geometry of the string landscape and the swampland. Studies on moduli-dependent KK towers and the swampland distance conjecture on the quintic Calabi-Yau manifold are also referenced. The paper leverages research on mirror symmetry, mirror maps, and applications to Calabi-Yau hypersurfaces and complete intersection Calabi-Yau spaces. Arithmetic properties of curves of genus 1, the SAGE mathematics software system, and Casimir energies for 6D supergravities compactified on T. 2, Z, N. With Wilson lines are also cited. Furthermore, the authors reference works on mirror symmetry as T-duality, Calabi-Yau threefolds and complex multiplication, rational conformal field theories, and complex multiplication. Research on K3 surfaces, including complex multiplication, rationality, and mirror symmetry for abelian varieties and K3 surfaces, is also drawn upon. Additionally, the paper cites studies on singular K3 surfaces, lectures on K3 surfaces, and special hypergeometric motives and their L functions. Works on black holes and critical points in moduli space, as well as split attractor flows and the spectrum of BPSD branes on the quintic, are also referenced. By building upon these foundational studies, the authors aim to explore novel ideas at the intersection of machine learning, Calabi-Yau manifolds, and string theory, with potential implications for our understanding of the string landscape and the swampland.